Hey there. Going to go over a little bit of Precal review today. So let's go ahead and get started here. First problem, you have to find the x and y intercepts, domain and range of this function. You should recognize this function. It might be a little easier if you square both sides. So you get y squared is equal to 9 minus x squared, and then add the x squared over. X squared plus y squared is equal to 9. That's a circle. This circle is centered at 0, 0, and has a radius of 3, because this is the radius squared. So this right here, when you go backwards, when you take the square root of both sides, you actually get a plus or minus. That's how you get the whole circle. So this is actually a semicircle. So you definitely want to remember that this equation is a semicircle, because you can do geometry with semicircles, and there's a lot of good stuff you can do there. And this is specifically the top half of the semicircle, because it's a positive square root. If they wanted the bottom half, they would have given us the negative square root. All right, so I'm just going to come over here and go ahead and graph this, and then we'll be able to fill these in pretty easily. So radius center at 0, 0, so there's that. Then I'm going radius of 3, so I'm going to negative 3. I'm going to go out to positive 3, and I'm going to go up on the y-axis to positive 3 as well. And that's it. All right, so it has two x-intercepts at negative 3, 0 and positive 3, 0. It has one y-intercept at 0, 3. Domain, we go from left to right, so it has a domain from negative 3 to positive 3. Both endpoints are included. And then range, we go from bottom to top. So we go from 0 up to 3. And again, both points are included in that. Right. Piecewise function. So just have to graph this one. We're going to graph this quadratic equation left of 0 and graph this linear function right of 0. So I usually just start by plugging in 0. That gives me a point. So if I plug in 0, 0 minus 1 is a negative 1. All right, this one's equal to 0. So we get a closed circle there. And then since I know I'm going left, less than 0 is left, I'm going to plug in a couple more points. So if I plug in negative 1, negative 1 squared is positive 1, minus 1 is 0. If I plug in negative 2 squared is 4, 4 minus 1 is 3. All right, and we know what a parabola looks like, so I'm not going to plug in negative 3, but you could keep doing that if you need to. So there's that. All right, same thing here. Plug in 0. 0 minus 2 is negative 2, but this one's not equal to. So make sure on that one you put an open circle. Okay, they can't both be closed circles, because then it would not pass the vertical line test. It wouldn't be a function anymore. So they can only let one of them. They could both be open, or one's closed, one's open. Just can't have both closed. All right, now I could do the same thing and just plug in some numbers, like 1, 2, 3. But this is a linear function. It's a lot easier just to use your slope, rise over run, and plot the points that way. So up 1, right 3. And I'm going to go ahead and do one more. I need a little more room here. Up 1, right 3. And we have our linear function going to the right of 0, because x is greater than 0, greater than goes to the right. All right, next. So back to finding some x and y intercepts. Now we have some asymptotes. We have a rational function here. So we're going to find our vertical and horizontal asymptotes and a slant asymptote if that's applicable. So let's get to that. First thing they ask about is horizontal asymptotes. So anytime you need to do a horizontal asymptote, you're looking at top heavy, bottom heavy, or balanced. And horizontal asymptotes happen when it's bottom heavy or when it's balanced. A slant asymptote happens when it's top heavy. Okay, so this one is balanced. The exponents are the same number. So we divide the coefficients in front. So 3 divided by 1. So our horizontal asymptote is y equals 3. Okay, if it's bottom heavy, that's automatically y equals 0 every time. All right, and then if it's top heavy, we'll see an example right down here for that. All right, vertical asymptotes come from your denominator. So I'm actually going to factor this. The numerator can't factor, so we'll leave that alone. But this can factor into x plus 2 times x minus 2, difference of squares. All right, and you set your denominator equal to 0. Whenever your denominator is 0, that will produce a vertical asymptote. I should be a little more specific there. When the denominator is 0 and the numerator is not 0. So you can't have 0 over 0. That would be something else. But when your denominator is 0 and your numerator is not 0, you get a vertical asymptote. So we're just going to do this in our head. -2 would make that one 0, and +2 would make that one 0. And if I plug in 2 or -2 to the numerator, I would not get 0. So that's how we know they're vertical asymptotes. All right, you cannot have a slant and a horizontal. It's either or. So since we had a horizontal asymptote, I know that there is no slant asymptote. All right, your x-intercepts come from the numerator. This is, you set y equal to 0. So if I plugged in 0 for y, I would say this whole fraction right here is equal to 0. All right, I'm going to erase that because I don't want it to say that right there, but that's what we're doing. And when you have a fraction equal to 0, the numerator is the part that would make it equal to 0. So really all we have to do is set that numerator equal to 0 and divide by 3, take a square root. You're going to get x equals 0. So your x-intercept is 0, 0. All right, a y-intercept is when you get x is equal to 0. So for this one, you plug in 0 for x. All right, for this one, we plugged in 0 for y, and we had to solve an equation. This one, you plug in 0 for x, and we get f of x is equal to 3 times 0 squared over 0 squared minus 4. And we get 0 on top and -4 on bottom, which is equal to 0. And that makes sense because if 0, 0 is an x-intercept, that's also your y-intercept. Remember, a function can only have one y-intercept. You can have a lot of x-intercepts, but you can only ever have one y-intercept, because if there were two y-intercepts, it would not pass the vertical line test. It wouldn't be a function anymore. So if you see that you get 0, 0 for the x-intercept, just know that's going to be your y-intercept as well. But there's the work to show you how to get that. All right, so let's start plotting this stuff. We have a vertical asymptote at x equals 2. We have another vertical asymptote at x equals -2. We have a horizontal asymptote at y equals 3. We have our x and y intercept here at 0, 0. All right, so what this tells me is that I have one of my curves. The curve that's in between the two asymptotes is down here. It's not up here because it has to go through this point, and it's not going to go through the asymptote. So you're just going to follow that asymptote. You're going to hit that point, and you're going to go back down. All right, I'm not too concerned about getting a bunch of points here. How did I know it's a parabola shape and not something else? It doesn't really make sense to be anything else, right? This point's right in the middle of the two asymptotes. So it wouldn't really make sense to like go up like this and then down and then up and something like that. Weird. All right, that's not going to happen. All right, so just pick the most standard looking curve that's going to go through that point. All right, now where do the other curves go? It can't go up here because that would fail the vertical line test. So we need a curve on the left side, either top or bottom, and we need a curve on the right side, either top or bottom. All right, and so the way you figure that out is called togetherness. That wasn't an option over here, but I'll write it here. Back when you did radii in Algebra 2 and you did radii again in Precal, the T in radii stood for togetherness. And what that meant is if it has togetherness, that means it comes together at an asymptote. So togetherness would mean that our curve would be right next to it. Since this is in the bottom, this would be in the bottom. Same thing over here. If there's no togetherness, then they're not right next to each other. So that means the curves would be in the top. All right, this one does not have togetherness. So how do you tell? You look at your original equation. The factored form is better. And if your factors are perfect squares, so like if this had been x plus 2 squared and x minus 2 squared, that would be togetherness. But ours were not squared. So this has no togetherness, which means that this curve on the left side cannot go in the bottom because that would be togetherness. So it has to go up here. And same thing on the right side. This curve, no togetherness, cannot go in the bottom. So it has to be right there. Okay, another way to do that, if you don't like togetherness, is to plug in a point. You know that this point right here is x equals 3. So plug in 3. 3 squared is 9, times 3 is 27. And then this would be 3 squared is 9, minus 4 is 5. So 27 over 5, which is what? 25 over 5 is 5 and 2/5, so 5.4. And so if you go 3, this is 1, 2, 3 to that asymptote, 4, 5.4. So right there would be like 5.4. So that's another way you could do it. You could just plug in numbers, and if you plug in -3, you get the same result at 5.4 number. So that's another way you could figure out that it's above the curve, above the asymptote instead of below the asymptote. All right, let's go to the next one. Okay, so same deal here. We're doing all the same stuff. We talked about horizontal, top heavy, bottom heavy, or balanced. This one is top heavy. Top heavy means we have a slant asymptote. So there is no horizontal asymptote. Remember, you have one or the other, either horizontal or slant, not both. Okay, vertical asymptote comes from the denominator. So x is equal to 1 for that. If I plug in 1 to the top, I do not get 0. So that's how I know that it's a vertical asymptote, not a hole. A hole is what happens when you get 0 over 0. All right, so how do we do the slant asymptote? We're going to have to do some division here. So I'm going to show you a couple different ways just because we're reviewing. So this is long division. Long division works on every problem. All right, so we're going to divide x minus 1 into x squared plus 2x. Notice I put a plus 0 because it was missing that last term. We're going to need a placeholder there for doing our work. All right, so what multiplies by x to equal x squared? Well, that would be an x. X times x is x squared. X times -1 is -x. And then when you divide, you subtract this. So we're going to switch the signs, minus and plus. X squareds cancel. 2x plus x is 3x. Bring down your plus 0. All right, do it again. What multiplies by x to equal 3x? Positive 3. All right, so we get 3 times x is 3x. 3 times -1 is -3. We're subtracting, so we're switch the signs, minus and plus. The 3x's cancel. That's how you know you did your step correctly, is if that first term always cancels out. And then we get 0 plus 3. We have no more terms to bring down, so this is our remainder. Which we would normally say, we would write like this, plus 3 over x minus 1, like that. But for slant asymptotes, you do not need a remainder. So you can ignore that. All you need is the x plus 3. That is your slant asymptote, y equals x plus 3. So it's a line, just like a horizontal asymptote's a line. So it's a line, but it's a linear function. It's a slanted line, which is why it's called a slant asymptote. All right, our x-intercepts. So remember, you're setting your function equal to 0, and when you do that, you take the numerator and set that equal to 0. All right, so we can factor x times x plus 2 is equal to 0. And so you get x is equal to 0, which means 0, 0. And then you get -2, or x is equal to -2, which is what makes that 0. So -2, 0 as well. All right, remember what I said about 0, 0. If that's an x-intercept, that has to also be a y-intercept. And again, you can verify by plugging in 0. 0 plus 0 would be 0 on top. 0 minus 1 would be -1 on bottom. 0 divided by -1 is 0. All right, we have all of our info now. Let's graph this thing. So x equals 1. Vertical asymptote there. Y equals x plus 3. So we have a y-intercept of positive 3 and a slope of 1. So 4 and over 1 right there. I'm going to go down and left. Do that a couple times. I think I'm going to go all the way over here to the x-intercept. It's the x-intercept of our asymptote, not an x-intercept of our graph. All right, now for the x-intercepts of the graph, 0, 0, and -2, 0. And so what that tells us is that one of the curves is right here in this section here. And again, you don't have to be super perfect. Just kind of follow the asymptote. Make sure you cross through the points. Something like this. And you're good. All right, now where does the other curve go? So it can't go on top because that would fail the vertical line test. Okay, so we're over on the right side. Is it top or bottom? We come back to that togetherness idea. Okay, is the denominator a perfect square? No, it's not a square at all of any type. To be a perfect square, we'd have to have parentheses and have a squared on the outside like that, and it doesn't. So no togetherness. which means we cannot put the curve on the bottom, so that would be right next to this one, so it's got to go up here. And again, just kind of follow the asymptotes like that, and you're good to go. All right, let's do some inequalities. As you know, this is going to have, we're going to do some number line analysis here, and that has big implications in calculus. We use that number line analysis quite a bit, so this is just kind of practicing that idea. All right, so anytime you want to solve a polynomial or really any type of equation, it's most likely a good idea to get it equal to 0 first. So I'm going to move that 12x over. X cubed plus x squared minus 12x. And we're going to pretend it's equal to 0 for the moment, and I'll come back to that. Actually, I'll write it less than or equal to. But we are going to solve it like an equation first, and then we worry about the inequality at the end. All right, so we need to do some factoring here. I can take an x out. Then we can factor that quadratic, x plus 4 and x minus 3. All right, and this is where we're going to pretend it's an equal sign. We get 3. We're going to call these critical numbers. X equals 0, x equals negative 4, and x equals 3. It's the 3 values that make our factors 0. All right, now here's where the number line happens. So this is how we're going to determine what our actual answer is for the inequality. So put these 3 numbers on a number line. Make sure you put them in the right order, negative 4, 0, and 3. All right, I'm going to put circles on my number line. This is an equal to, so they get closed circles. And then we want to figure out where this function is less than 0. So we want negative values. So we're going to test numbers in each region in between these. So pick the easiest number possible, negative 5, negative 1, positive 1, and positive 4. Okay, you can pick any number you want in that region, but you want to try to pick the easiest ones to use, which is usually the next closest integer. All right, so we're going to plug these into this form, the factored form. It's much easier to do it that way because if you plug it into the original, you have to like really figure out like what's negative 5 cubed and negative 5 squared and negative 12 times negative 5, and then add them all together, and it gets kind of tough, and we don't have a calculator here. So it's much easier to do it down here because you don't even need to worry about what the numbers are. You just care about the signs. If I plug in negative 5, I have a negative right there. If I plug in negative 5 plus 4 is a negative. Negative 5 minus 3 is a negative. So it's a negative times a negative times a negative, which would be a negative. If you have an odd number of negatives, it stays negative. If you have an even number of negatives, it's going to become positive. All right, so let's do the same thing for negative 1. So that would still be a negative there. Negative 1 plus 4, that would be a positive. Negative 1 minus 3 would be a negative. Even number of negatives, so that's a positive right there. Positive 1, that would now give me a positive here. 1 plus 4 is positive. 1 minus 3, negative. Only a single negative means that's going to be a negative, and then plug in 4. Positive, positive. 4 minus 3 is positive. So we're back to positive there. All right, we're looking for less than 0, so we want the negative section. So we want that section there, and we want this section here. So a couple different ways you can write your answer. X is less than or equal to negative 4, or 0 is less than or equal to x is less than or equal to 3. Or if you like interval notation better, you could do negative infinity to negative 4 included, u, and then included 0 to 3 included. So that's a couple different ways to write it. I don't really care how you write your answers. Whatever you're more comfortable with is fine with me. All right, this one's already factored, so we can just find our critical numbers right away. So x equals negative 3 halves minus 3 divided by 2, and x equals positive 4. So we're going to put those on our number line. We're trying to figure out where this is less than 0. And since it's just a regular less than, not equal to, we want open circles. All right, and I'm not going to write my numbers that I'm testing. We'll just do that in our head, but we're doing the same thing here. Now, before we start, I want to point out that this last problem is a pretty standard problem. And see how the signs alternate? That happens most times. But there are problems that are not standard. All right, and letter B is one of those. The reason this is not standard is because this factor is squared. So most of the times the factors are not squared, they're linear. And so every time if you plug in a negative number, you get a negative, and if you plug in a positive number, you get a positive. Well, over here, doesn't matter what I plug into this one. If something is squared, that is always a positive, no matter what. So that's going to mess up our alternating thing, just so you know. All right, now this is an odd exponent. An odd exponent is just like having a 1 as an exponent on this. Odd exponents are going to keep whatever sign you get when you plug in. All right, so everything's going to be determined by this factor right here. All right, so this is negative 1.5, so I'm going to do negative 2. So 4 minus negative 2 would be 4 plus 2, which is 6, so that's a positive. So we're going to get a positive there. We'll go 0 in the middle here. So 4 minus 0, that's positive. So we get a positive again. So notice how it didn't alternate. Yep. And then 5. 4 minus 5, that is a negative. Positive times a negative is a negative. And we want where it's less than 0, so we want that region right there. And that's our answer. 4 to infinity. Parentheses on both. Or we could do x is greater than 4. Either one there. All right, what if it's a rational function like this? You pretty much do it the same way. I am going to start by factoring top and bottom. So this is x minus 4 and x minus 5 on top. And then we get x plus 3 and x minus 3 on bottom, greater than or equal to 0. And so we actually get 4 critical points. X equals 4, x equals 5, x equals negative 3, and x equals positive 3. All 4 of these are going to go on our number line. Make sure you get the right order. Negative 3 first, and then we have 3, 4, 5. All right, now you have to be really careful about your circles here. So it's an equal to. So that tells you closed circles, just like we did on letter A. But the denominator, the 2 critical points we got from the denominator, you can never be equal to those. Because if you were equal to 3, you would get a 0 in the denominator. And you're never allowed to have 0 in the denominator no matter what. So the 3 and the negative 3 have to have open circles, even though it says equal to there. The 4 and the 5, those follow whatever this says. So those are going to be closed circles. So just be careful on the rational functions. Whatever you get from the denominator, those have to be open no matter what. All right, now we have to test a point in each region. And again, we're just going to plug it into the factored form here. And odd number of negatives is a negative. Even number of negatives is a positive. All right, so we're going to plug in negative 4 up here. So negative 4 minus 4 is a negative. Negative 4 minus 5 is a negative. Negative 4 plus 3 is a negative. And negative 4 minus 3 is a negative. 4 negatives makes a positive. All right, I'm going to plug in 0. 0 minus 4, negative. 0 minus 5, negative. 0 plus 3, positive. 0 minus 3, negative. 3 negatives make a negative. All right, now we have to do decimals, but it's okay because we're just doing positives and negatives anyway. So 3.5, 3.5 minus 4, negative. 3.5 minus 5, negative. 3.5 plus 3, positive. 3.5 minus 3, positive. 2 negatives make a positive. 4.5. All right, so 4.5. 4.5 minus 4 is a positive. 4.5 minus 5 is a negative. 4.5 plus 3 is a positive. 4.5 minus 3 is a positive. Single negative is a negative. 5.5, I think you know where this is going. Positive. 5.5 minus 5 is a positive. 5.5 plus 3 is a positive. 5.5 minus 3 is a positive, so that's a positive. We want the sections where this is greater than or equal to 0. So we want the positive sections. That's here. That's here. That's here. So we get x is less than negative 3, or 3 is less than x is less than or equal to 4, or x is greater than or equal to 5. Interval notation version, negative infinity to negative 3 excluded, u, excluded 3 to 4 included, u, included 5 to infinity. Infinities are never included. All right, one more factoring problem here. So anytime you have 4 terms, you're going to factor by grouping. So you're going to group the first two terms together. You're going to group the second two terms together. Take out the GCF. These two terms have an x squared in common. That leaves you with x plus 3. These two terms have a 4 in common, but if you have a negative in front, it doesn't matter if they're both negatives. It only matters if this term right here is a negative, you have to take out the negative as well. So we're going to take out a negative 4. That's going to leave me a positive x, and then you're dividing, remember, negative 12 divided by negative 4 is positive 3. The way you know factor by grouping worked is if your two parentheses are the exact same thing. They have to be the same. If they're not, you either did something wrong or factor by grouping doesn't work. That is certainly a possibility. Okay, but ours are the same. It works. So we're going to continue factoring. These are two terms now. This is a term right here. Then you have your minus sign, and then this is a term. What do these two terms have in common with each other? They both have an x plus 3. What's left over if we take out the x plus 3? Well, this term has an x squared left over. This term has a minus 4 left over. All right, we can factor one more time. X plus 3. This is a difference of squares. X plus 2 and x minus 2. So we get our critical values of negative 3, negative 2, and positive 2. Put those on our number line. We have a regular greater than, so all open circles. Test points, negative 4 would be a negative times a negative times a negative, which is a negative. Negative 2.5, gotta be careful here, as people mess it up on the negative side a lot. So negative 2.5 would be in between those, which would be a positive, and then a negative and a negative, which is a positive. We'll go with 0 here, a positive and a negative, which is a negative, and then 3. Positive, positive, positive. We want greater than 0, so we want this section here and this section here. So negative 3 is less than x is less than negative 2, or x is greater than 2, or excluded negative 3 to negative 2, excluded u, excluded 2 to infinity. All right, we're going to do a little trig here, and then we'll finish up with an exponential and some limit problems. All right, so trig questions. We're still really doing algebra, it just has trig in there instead. So this is a quadratic equation, 3 terms, squared, first power, constant. So we're going to factor 2 cosine x times 1 cosine x. If you multiplied those together, you would get 2 cosine squared. All right, now we need two terms that multiply to negative 5 and add up to negative 9. Obviously, the two numbers that multiply to 5 are 5 and 1. Those do not add up to 9, but remember, one of them, whatever you put in this part, is going to multiply by 2. So I think I want a negative 5 there. That's going to give me negative 10. And then if I add 1 to negative 10, I get negative 9. Which is what I want. I have to have them be opposite signs because I had to get a negative 5 here instead of a positive 5. So I think I'm good to go. All right, so if we solve this, I end up getting cosine x is equal to negative 1/2. And then I end up getting cosine x is equal to 5. All right, so from your unit circle, cosine is equal to negative 1/2. Notice we're on an interval up here, 0 to 2 pi only, 2 pi not included. All right, so cosine is equal to negative 1/2. Cosine is negative. Cosine is the x-coordinate, so it's negative in quadrant 2 and quadrant 3. And cosine is equal to 1/2 at the pi over 3 locations. So that's x equals 2 pi over 3. And in quadrant 3, that would be 4 pi over 3. All right, over here, remember that cosine has a range. Negative 1 is less than or equal to cosine x is less than or equal to positive 1. It oscillates between negative 1 and positive 1. So would it be possible for cosine to equal 5? No. Cosine, the maximum of cosine is positive 1. So this actually has no solution, which means these two are the only solutions for this equation. All right, next one, you're going to have to remember trig identity. Sine of 2x. This is a double angle formula. This one shows up quite a bit, so I definitely recommend memorizing this one. Sine of 2x is equal to 2 sine x cosine x plus cosine x is equal to 0. The reason that's helpful is because we can now factor out a cosine. So I end up with cosine x is equal to 0, and I end up with sine x is equal to negative 1/2. Subtract the 1, divide by 2. All right, so cosine x is equal to 0 at the pi over 2 locations. So that would be pi over 2 and 3 pi over 2. Sine x is equal to negative 1/2. So sine is negative in the bottom part of the unit circle. So that's quadrant 3 and quadrant 4. And sine is equal to 1/2 at the pi over 6 locations. So quadrant 3 would be 7 pi over 6, and quadrant 4 would be 11 pi over 6. So 4 solutions on there on that one. All right, this is another double angle formula. Now, cosine of 2x actually has 3 versions. Okay, so I think I'm going to make a little note over here. Here, I'll call it trig identities. All right, so we just did sine of 2x is equal to 2 sine x cosine x. All right, so cosine of 2x. So the main one is cosine squared of x minus sine squared of x. Sorry, I'm squeezing them in there. All right, but then remember that there's this identity, that sine squared plus cosine squared is equal to 1. And then you can manipulate that. Or okay, so if you applied these to this, so let's say we replaced cosine squared with 1 minus sine squared, you would get 1 minus sine squared, which would be 1 minus 2 sine squared. Or if you replaced sine squared with 1 minus cosine, you would get cosine minus 1 plus cosine squared, because the negative times a negative. So that would be cosine squared plus cosine squared, which would be 2 cosine squared minus 1. Okay, so there are 3 versions of the cosine of 2x. So you want to pick which one's going to be most beneficial to you. So let's go back and look at our problem over here. On the other side of the equation, I have a sine x. So if you're not going to be able to factor out a common factor, like we were able to factor out the cosine, then you want to change everything to be the same function. So since I have a sine x over here, I want everything on the left side to be a sine as well. So I'm going to pick the 1 minus 2 sine squared version. All right, then I'm going to move everything to one side. I'm going to move these two to the right because I want my sine squared to be positive. So that's going to be a positive 2 sine squared x. Then I have a positive sine x already over there. Then I'll have a minus 1. And I'm just writing them on the left side because I like it better that way. All right, quadratic equation again. So we're going to factor. This one's pretty simple because we have a negative 1. We know it has to be a 1 and a 1. That's the only option. We know they're opposite signs, so the only struggle here is figuring out which one's a plus and which one's a minus. We want to end up with a positive sign in the middle. So we want the one that's multiplying by 2 to be a positive, and the one that's multiplying by 1 to be a negative. Positive 2 minus 1 would be positive 1. So I end up with sine x is equal to 1/2. And sine x is equal to negative 1. All right, so sine is positive in quadrant 1 and quadrant 2. Sine is equal to 1/2 at the pi over 6 locations. So quadrant 1, that's pi over 6. Quadrant 2, that's 5 pi over 6. Sine x is equal to negative 1 at 1 location, 3 pi over 2. All right, last one here for the trig. This is a triple angle. I'm sure that there's a formula out there, but it is not one that you're expected to know. I don't know it off the top of my head. I don't even know if there is one, to be honest. We don't need it on this problem. So you're going to just do basic algebra here. So you're going to get the sign by itself, which means we'll have to add the square root of 3 and then divide by 2. So we get the square root of 3 over 2. All right, that is super useful because that's a unit circle value. So whatever's on the inside of your trig function, you can set that equal to your unit circle angle values. So sine is positive in quadrant 1 and quadrant 2. Sine is equal to square root of 3 over 2 at the pi over 3 location. So this is pi over 3 in quadrant 1, and this is 2 pi over 3 in quadrant 2. All right, now the trick here is that we're not done. This is 3x is equal to this. So we want to end up with x is equal to, so we have to divide by 3. So we get pi over 9 and 2 pi over 9. Now, the trick here is that we're not done yet. Remember, we want all possible solutions that are in the 0 to 2 pi interval. Okay, so normally we just get the unit circle values, that's x, and we're done. All right, but since we had to divide by 3, there are actually more solutions. So remember, you have an infinite amount of solutions to these equations. If they don't give us an interval to be on, then you could just keep on saying solutions. So we could go an entire 2 pi around. Okay, so an entire 2 pi around would be 6 pi over 3 if we got a common denominator. So the next answer in this same location would be 7 pi over 3. It's pi over 3 plus 2 pi. Okay, I'm trying to figure out where to write this. I'll write it over here. Pi over 3 plus 2 pi. Okay, and then I'm getting a common denominator, 6 pi over 3. That's equal to 2 pi. So that's how I got that. Now I do the same thing for 2 pi over 3. Add 6 pi over 3, and I get 8 pi over 3. Now those are not in the original. Those are not in the interval. Those are bigger than 2 pi. But when I divide by 3, I get 7 pi over 9 and 8 pi over 9. Those are in the interval. Okay, and in fact, we can do it again. So I can add 6 pi over 3 again. So that would be 13 pi over 3 and 14 pi over 3. Divide by 3, and you get 13 pi over 9 and 14 pi over 9. Okay, and 2 pi, if you got this over 9, see all of our answers are over 9, 2 pi is equal to 18 pi over 9. So as long as our answers are smaller than 18 pi over 9, they are in the interval. Okay, so you can try it one more time, add another 6 pi over 3, but you can see if you add 6, you're going to get 19 pi over 3, which even if you divide by 3, you'll end up with 19 pi over 9, and that's too big. So that's how we know we're done. These are the answers. Okay, a quick way to kind of know how many answers you're going to have. You normally get 2 answers when you solve this problem. Your angle was multiplied by 3, and so we got 6 answers. Instead of 2 answers multiplied by 3, you get 6 answers. So that's a little quick way you can kind of think about how many solutions are there going to be to this problem. And so that's how you can handle those coefficients inside the angle like that. All right, quickly, we're going to solve this out. It says use your calculator, so I'm going to get that loading up while we work the problem. So we still have to do some algebra here before we use our calculator. This is a quadratic equation. Squared, first power, constant. So we factor. We get e to the x times e to the x. Okay, remember, e to the x times e to the x, you add the exponents together. That's e to the x plus x, which is e to the 2x. All right, then we need numbers that multiply to negative 10, add up to negative 3. Should be minus 5 plus 2. All right, that's equal to 0. So then we end up with e to the x is equal to 5, and e to the x is equal to negative 2. The way that you solve this equation is you take a natural log on both sides to cancel out the e. So you get x, natural log and e cancel, x equals natural log of 5, and x equals natural log of negative 2. All right, so got my calculator ready here. Press Control, e to the x, natural log of 5. I'm going to hit the decimal right there to give me decimal form, 1.609. All right, and you're going to do this next one, and we're going to get a little issue here. Error, non-real result. So just a reminder that the natural log function has a domain of 0 to infinity, and 0 is not included. So anytime you're dealing with logs, you are never allowed to plug in a negative number, and you're never allowed to plug in 0 to a log. So if you're ever solving an equation, you see that, just know that that is not going to be a solution. That's an extraneous solution. This factor right here has no solution to it, so we only get the one viable answer, 1.609, which is equal to the natural log of 5. All right, finish this up with a couple limit problems here. Remember, your first line of defense on a limit problem is to plug the number in. So if I plug in -4, I'm going to write it out like this. The limit as x approaches -4 of x cubed plus 64. Well, -4 cubed is -64 plus 64 is 0. All right, and then the limit as x approaches -4 of x squared minus 16. -4 squared is 16, minus 16 is 0. So this is 0 over 0. So that means we have more work to do. All right, the more work to do on this one is factoring. So the limit as x approaches -4. This is a sum of cubes. So it's a formula you have to know. I'll write it down here. A cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. You can also do a difference of cubes. The only thing that changes are the signs. The signs follow an acronym: SOAP, same sign, opposite sign, always positive. So same sign was plus, opposite sign was minus, always positive. So this one's same sign is minus, opposite sign is plus, always plus. And this is the same format: a squared, ab, b squared. So this is going to be a is x. It's the cube root, if you will. And then the cube root of 64 is 4, which is b. So it's going to be x plus 4 times x squared minus 4x plus 16. Then on the bottom, that's a difference of squares. So you get x plus 4 and x minus 4. The x plus 4s can cancel. Plug your number in. -4 squared is 16. -4 times -4 is 16 plus 16. -4 minus 4 is -8. So you end up with positive 48 divided by -8, which is -6. All right, this one, same deal. They're really emphasizing writing out the two separate limits on this year's test, so that's why I'm making sure we do that this year. Square root of x plus 4 minus 2. I plug in 0. Square root of 4 is 2, minus 2 is 0. And then the limit as x approaches 0 of x is equal to 0. Just plug it in. So this is another 0 over 0, which means we have more work to do. So the more work to do on this one is to multiply top and bottom by the conjugate. So we're multiplying by the square root of x plus 4 plus 2. So we get the limit as x approaches 0. When you multiply by the conjugate, you do a squared minus b squared. So a squared would just be x plus 4 minus b squared would be 4. Denominator, don't multiply. Leave it with parentheses like this. The reason for that is because everything should cancel, basically. So plus 4 minus 4, that'll always happen on these conjugate problems. And then whatever's left should cancel on the denominator like that. Okay, so now we have the limit as x approaches 0 of 1 over the square root of x plus 4 plus 2. Square root of 4 is 2, plus 2 is 4. So our answer is 1/4. All right, enjoy that Precal review worksheet, and I'll see you on the next video.